Delaware Tech, Chemistry 100, Chemistry 110, Neutralizations and Titrations. So a neutralization reaction is a reaction where you're adding exactly the same amount of base in terms of the moles of the hydroxide as you are to the amount of moles of acid in terms of the moles of the protons that the acid produces. And when those two equal each other, you have neutralized your reaction. You've neutralized the acid with the base, you've neutralized the base with the acid. And when you're using hydroxy bases, we always will end up with a salt of some type of ionic compound, and the water is formed from the addition of a proton, an H+, plus a hydroxide, an OH-, which end up forming a covalent bond between these two ions. And this is very favorable because it releases a lot of heat. So, when this is done drop-wise, in other words, you're taking some acid in a beaker or a flask, as shown here, and you've got your base in a container above it. This is called a pipette, or this is called a burette, and this burette holds a certain amount of base, and it has a stopcock which you can turn and allow one drop at a time to come out, and you watch it drop by drop until your acid is neutralized, and you stop exactly at the moment that it's neutralized, and then you measure how much of the base that you used, and you know the concentration of the base, and you can calculate what the concentration of your unknown acid is. Now, if you do this dropwise, if you do a neutralization dropwise, we call this a titration. So examples of the chemistry of what you're using would be starting with an acid and adding a base, or starting with a base and adding an acid. You could do the exact same thing, just switching the two in the flask and the burette. So in my first example here, I have nitric acid, HNO3, reacts with potassium hydroxide, KOH. And in this case, we're going to get, in all of these cases, since we're dealing with hydroxy bases, we're always going to get a double replacement reaction where we're going to produce some kind of ionic salt and water. So you see we've got a proton derived from the acid and an OH derived from the potassium hydroxide. They'll form water, and the remaining two ions will form a salt. And in this case, the salt is potassium nitrate, what used to be known as saltpeter. This is the active ingredient in gunpowder. About 75% of gunpowder is potassium nitrate. You can always look up what the rest is. I'm not going to discuss it right now. But the other product here is water. And I've written it as HOH to remind you that the H2O is actually formed from an H ion, an H+ ion, and an OH- ion. The second example we have is hydrochloric acid with barium hydroxide. Now, barium hydroxide has two hydroxide groups in it, but the barium will find the chlorine, the chloride resulting from the hydrochloric acid, and form barium chloride, and water will be formed. Now, notice that it's not balanced as it is, so now I've added the 2's here to balance it, and you see we now have 2 protons added to 2 hydroxides to make 2 waters, and then the remaining barium will mix with the 2 chlorides to form our salt. So everything is now balanced. If we look at the next one, sulfuric acid, this has 2 protons, and strontium hydroxide, which has 2 hydroxides. And since it's a 2 to 2, we don't need to balance it, and we're going to get strontium sulfate as our salt, and 2 waters as a result of the 2 protons reacting with the 2 hydroxides. Another one is sulfuric acid, but now with sodium hydroxide, which only has 1 hydroxide. So you can guess ahead of time that we're going to need 2 sodium hydroxides to provide our 2 hydroxides for our 2 protons to make our 2 waters. And the last reaction is phosphoric acid, which is a triprotic acid, 3 protons, with barium hydroxide, which is a dihydroxy base. So we've got 3 protons here, and we've got 2 hydroxys here. Well, we're still going to make our salt, and if you actually balance the barium +2 ion with your phosphate -3 ion, and did your crisscross simplify to figure out what your final formula is, you'll see that you end up with 3 baryons in your salt and 2 phosphate groups in your salt. But in fact, you can figure that out even before you do the barium phosphate determination of the formula by noticing I have 3 protons here and 2 hydroxides, so I need 3 of the 2 and 2 of the 3. That would be a total of 6 waters that are formed in this reaction. And again, these are all double replacements because in each case, the cations, which are the positive charges in the bases, and the protons in the acids, switch places, and the anions switch places. The anions would be the hydroxide in the bases, and whatever is left in the acids. So in the case of nitric acid, it's nitrate, chloride and hydrochloric acid, sulfate in sulfuric acid, and phosphate in phosphoric acid. And that is how you determine your products.